Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 8th video lecture. And we've been talking about differentiation, about vector value functions by complex value functions. And we've had some analogous facts to what we had about real valued functions in terms of differentiation. But I want to start off today with two examples that illustrate two facts that we had for real valued functions don't apply to complex valued functions in terms of differentiation. So as an example, to start off with, the first example is we will define f of x equal to e to the ix, which is the same thing as cosine x plus I sine x, where x is an element of real numbers. And then we're going to make some observations about this. First of all, note that f of 2 pi, so that would be 1, that's 0 here, so that would just be equal to 1. And f of 0, that would also be equal to 1. Okay, so what we have is f of 2 pi minus f of 0 is equal to 0. That's 1/2. Now, it turns out that f prime of x is going to be equal to the derivative of cosine, which is going to be minus sine of x plus, and here I times the derivative of sine, which is cosine of x. And if we consider and observe or note that the absolute value of this complex number is equal to it's equal to the square root of minus sine x to b squared plus cosine x to b squared, which equals to 1. Then, or thus, I should say that the absolute value of the derivative of this function, complex absolute value, is never 0. So that says, so this is, so I should say is never 0. It's never 0. And that's true for all x element of R. So that says that f prime of x is never 0. So considering f equal to e I x, that's f of x, on the closed interval from 0 to 2 pi, then turns out that f is differentiable on the open interval from 0 to 2 pi, and f is continuous on the closed interval from 0 to 2 pi, but there is no x in the open interval from 0 to pi, such that f of 2 pi minus f of 0 is equal to 2 pi minus 0 times f prime of x. There is no x that makes that true. Okay? And that's telling us, thus, the mean value theorem is not true for complex value functions. Next thing I want to do is look at an example about a complex function, two of them, and talk about what this example says for low cost rule. So as an example, if we look at on 0 to 1, that interval, we define f of x to be equal to x, and g of x to be equal to x plus x squared times e to the I over x squared. So we look at those two functions, and we think of them as complex value functions, even though the f of x is real value. We think of real numbers as complex numbers. So we know the limit as x goes to 0 of f of x over g of x is equal to the limit as x goes to 0 of x over x plus x squared times e to the I over x squared. Now you can factor out an x in the bottom, and that cancels with an x in the top, so what you get is the limit as x goes to 0 of 1 over 1 plus x times e to the I over x squared. Okay. Now, I want to do a plane here, so I'm going to plane something we need. I want to plane that the limit as x goes to 0 of x times e to the I over x squared, I want to claim that that equals to 0. Let's start the proof of this claim. Okay. So we're talking about a limit of a function, and we're going to let epsilon be greater than 0 be given. Okay. We need a delta bigger than 0, such that for all x in 0 to 1 with 0 less than the absolute value of x minus 0 is less than delta, this delta we're looking for. Okay? Delta is visible. Then the metric in the complex plane, complex numbers, metric in the complex numbers. Then x times e to I x minus, this should be squared here, this absolute value, this is the metric, it's the distance between these in the complex plane, this absolute value, will be less than epsilon. That's what we want. So we want to make this thing less than epsilon. So let's look at it for a second. Note this absolute value of x times e to the I x squared minus 0, this absolute value, complex absolute value, is equal to, well, it's just the complex absolute value of x times e raised to the I over x squared. Okay. And here, when you think of these as two things, and one of the things we proved with this absolute value, sometimes they use double bars, okay? That is absolute value of x in complex numbers times the absolute value of e to the I over x squared in complex numbers. And x is can be thought of as a real value function as well, and applying the absolute value to it is the same thing as absolute value in R. Okay? And then times, here, what this is going to be, if you remember how we define e to the I times something, so the something is 1 over x squared here, it's going to be cosine of 1 over x squared plus I sine of 1 over x squared. And its complex absolute value is going to be cosine squared of 1 over x squared plus sine squared of 1 over x squared, square root of that. And that's equal to the absolute value of x in R. And then this quantity right here, I mean, cosine squared plus sine squared is the same thing as 1. It's the square root of 1, so we just get 1. And that's really equal to x minus 0 in R, just absolute value of x minus 0. And so what we have is this quantity that we want to be making less than epsilon. We know that it's less than this quantity, and this is the quantity we can control. So we let delta be equal to epsilon. Then I'll say for all x element of 0, 1 with x minus 0 in R, that's what it is less than delta, we have it be less than epsilon. Then x minus, well, I'll say this, x times e to the I over x squared is the same x. Minus 0 will be less than that quantity. This is in complex. This will be in reals, absolute value, which is less than delta, which is equal to epsilon. And so we'll get what we want. And so that tells us, I'm going to include your statement, it tells us that our plane is accurate. So that says that the limit, if x goes to 0, of x times e to the I over x squared does indeed equal 0. So that ends the proof of claim. Okay. Now, note g prime of x is going to be equal to 1 plus x squared times e to the I x squared. So I'm taking the derivative of this. So it will be times I. And then you write this down as x to the minus 2. So I multiply by minus 2. So let's say minus 2i. And then it'd be x to the minus 3. But I'm having to use the product rule in this aspect of taking the derivative of g. So then I'd have plus, and then we have 2x times e to the I over x squared. That's what we get. And that's equal to 1
And then if we simplify this a little bit and pull out an e to the I over x squared, which is from this term and this term, this x squared and this x to the minus 3 produces an x in the bottom. So if you will, we have, well, let's just write down the last term first. It'll be 2x, and then it'll be minus, here is 2I over x. Okay, that's what we have. Now, note that if you look at the complex absolute value of g prime of x minus 1, kind of work with this so that we can handle this minus 1 just a little bit. This is going to be equal to complex. It's going to be equal to the absolute value of e to the I over x squared times 2x minus 2I over x. Okay? It's in the complex plane. And here, that's equal to, well, it would be the complex absolute value of e to the I x squared times the complex absolute value of 2x minus 2I over x. And this guy, we've already shown that its absolute value is 1, so we just get 2x minus 2I over x, its absolute value with respect to the complex plane. And that's true for all x element of 0 to 1. Okay. Well, what we had was this absolute value of g prime of x minus 1. Well, that is going to be less than or equal to, so we have g prime of x absolute value, the complex number, plus the absolute value of 1, which is just 1. That part is greater than or equal to the absolute value of g prime of x minus 1 in complex, okay? So I'll say since. And that's by the triangle quality. And so here we have the complex absolute value of g prime of x plus 1 is going to be greater than or equal to what we said this was equal to, which was the absolute value in the complex plane, 2x minus 2I over x. And so the absolute value of g prime of x is going to be greater than or equal to the absolute value, this is in the complex plane, of 2x minus 2I over x in the complex plane. And this would be minus 1. Now this part is equal to, so this is the real part, that's the imaginary part, so it's the square root, this guy squared, so 4x squared, plus it's this 2 over x to be squared, so that's 4 over x squared, and then minus 1. And I want to tell you that this is going to be bigger than, so I'm going to make it smaller. What's smaller is if I took away the 4x squared from here, so it's, this is bigger than 4 over x squared minus 1, and that's equal to 2 over x minus 1. That's what we get because we're talking about x values in between 0 and 1. So, hence, the absolute value of g prime of x over, f prime of x over g prime of x. Now, f prime of x, this is the complex plane. F prime of x was equal to 1. This is equal to 1 over g prime of x, and that can be rewritten as 1 over g prime of x is absolute value, complex plane. And so this is the bottom, the denominator, is a real number. And what I know about that real number is that it is bigger than 2 over x minus 1. So it's bigger than. So this is going to be less than or equal to 1 over 2x minus 1. So I'm replacing the bottom with something smaller, so the whole thing got bigger. It's positive. The whole thing got bigger. And that's equal to, so getting a common denominator, this is 2 minus x in the bottom, and the top x. Okay. Now, the next claim that I will make is that the limit as x goes to 0 of f prime of x over g prime of x is equal to 0. So, we'll prove this using the definition of a limit of functions. We let epsilon be greater than 0. This is the proof of claim. Let me write this down. Okay. We let epsilon be greater than 0 be given. Okay. And so we need a delta. Greater than 0, such that for all x in 0 to 1, with, again, it would be x minus 0, this is an R, is less than delta. Then, the absolute value of f prime of x over g prime of x minus 0, and that's in the complex, will be less than epsilon. So here, since the limit, I'm not going to go through this very much, as x goes to 0 of x over 2 minus x. Look, as x goes to 0, we're thinking this is the real value function. The top's going to 0, the bottom goes to 2, so you just get 0. Okay, say that. Then, there exists a delta bigger than 0, such that for all x, did I say that was between 0 and 1? Yeah, I did. For all x in between 0 and 1, with 0 less than x minus 0 is less than delta, then f prime of x over g prime of x inside absolute values, this is complex absolute value in this case, which we know to be less than or equal to absolute value of x over 2 minus x, that's in the real setting, which we know to be, if x minus 0 is less than delta, we know we can make this guy be less than, well, minus 0, which is just this. It will be less than epsilon. And so, I've got this guy is less than epsilon, and that's the absolute value in the complex plane of f prime of x over g prime of x. So that says that the limit as x goes to 0 of f prime of x over g prime of x, that part's equal to 0. Now, this work here says that L'Hopital's rule doesn't hold for complex functions, but I won't remind you why. This is G prime here, didn't look too good. From our first claim, I didn't explicitly say this, what our first claim did for us, and I should have, but our first claim, from our first claim, here's what we get. The limit as x goes to 0 of f of x over g of x, which you might remember was equal to the limit as x goes to 0. It was 1 over 1 plus x times e to the I over x squared. And what we did in the first claim is we proved that the limit as x goes to 0 of just this part equals to 0. So this equals to 1. So look, the limit as x goes to 0 of f over g is equal to 1. But the limits of its derivatives over each other was equal to 0. And that indicates then, thus, this is an example, which indicates that L'Hopital's rule is not true for complex functions. Okay, even though the mean value theorem is not true for complex value functions, we do get an analogous theorem for vector value functions, and I'd like to look at it next. Here's what it says. It says, suppose M is a continuous mapping of A to B into RK, and F bar is differentiable in the open interval from A to B. Then there exists an X element of the open interval from A to B such that here F acting on B minus F bar times A acting on A. The difference between those in the norm of RK is going to be less than or equal to B minus A times the norm of F bar acting on X. That's what we have. And so that is, in some sense, like the mean value theorem, at least similar to it. We'd like to prove that. Okay. So to prove, we start off by letting Z bar. This isn't thought of as necessarily a complex number, it's a function, okay? and it's equal to, let's say Z bar of X is equal to, what it is, it's F bar of B minus F bar of A. So it's a constant function, if you will. And define is a constant function, but it's a constant function into RK, Z bar is. And define phi of T to be equal to Z bar dotted with F bar of T. So this is the inner product here between these two, acting on T, these two functions. Okay? And this is for T that's in between A and B. Okay, remember this inner product is going to yield a real value function. So this is an inner product of things in RK. So F of T, phi of T is a real function on A to B. Okay. Now, since Z bar is a constant function, okay, with Z bar going from the closed interval from A to B into RK, then Z bar is continuous. Okay. Since we look at F bar, so if we look at it and Z bar, Z bar of T are continuous on A to B, then by a fact already proven in analysis 1, that is Z bar inner product with F bar acting on T is continuous. It's continuous on A to B. Okay? So each one of these Z bar and F bar, they were continuous as vector value functions, but this is a continuous function that's a real value function. Okay? Okay. Also note, since Z bar is a constant function, then Z bar, again going from A to B into RK, is differentiable. On A to B open interval. Okay? And since this derivative is 0, since okay. So F bar, we're assuming by hypothesis is differentiable. So here's what we'll say. Then, or thus, Z bar dotted with F bar, inner product, acting on T, is differentiable on A. All right. T, okay, is continuous on the closed interval from A to B, continuous on the closed interval from A to B, and is differentiable on the open interval from A to B, and phi t and phi of t is real value. So we can apply the mean value theorem to phi of t. Okay. Then by the mean value theorem, okay, we have phi of B minus phi of A is equal to B minus A times phi prime acting on X for some, which equal to, let me say this. This is equal to B minus A, and this phi prime of X is going to be nothing more than Z times F bar prime acting on X. And that's true for some X element of the open interval from A to B. That's what we'll have. And the way we get this is by a fact we had in our last video lecture about taking the derivative of the inner product between vector value functions. Okay, now what we're going to concentrate on next, so we have phi of B, I should say, minus phi of A is equal to this quantity. Let's look at phi of B minus phi of A. Okay. So this is equal to Z inner product dotted with F bar acting on B minus Z bar inner product with F bar acting on A and what this quantity, the first quantity is going to be equal to, if we expand that, it's going to be so Z bar is nothing more than F bar acting on B minus F bar acting on A, inner product with, this is going to be F bar acting on B, and here this is minus Z bar, which is going to be acting on A, which is F bar acting on, this should have been, well, I think I did this a little too fast. Okay, so the way to think about this is this is, no, I didn't do it too fast, I'm sorry. It's F bar of B minus F bar of A, that's right. Inner product with F bar of B. And then minus, here again, we're going to have F bar of B minus F bar of A. That's what Z bar is defined to be of A. Remember, it's a constant function, so no matter what it was, it's this. no matter what the input value is. Inner product with F bar of A. Okay. Now, that's equal to, so the F bar of B minus F bar of A, and that's going to be, when you subtract them, you get one K tuple, and it's F sub 1 of B minus F sub 1 of A, comma, F sub 2 of B minus F sub 2 of A, comma, all the way up to F sub K of B minus F sub K of A. Okay. So that's that F bar of B minus F bar of A. And then we have to inner product that with F bar of B. And then from that, we're subtracting exactly this. So F1 of B minus F1 of A. And then F2 of B minus F2 of A, that's what we had, all the way up to F sub K of B minus F sub K of A times, here it's F bar of A. Now, we can rewrite this, this first quantity is one sum, so how do we do the dot product? We take each component from here times the corresponding component here. And so this would be F, I'll call it F sub I of B. So as I runs from 1 to K. F sub I of B minus F sub I of A, same I here. That's one of these components, okay, the ith component here, times the ith component there, which will be F sub I acting on B. Minus, similarly, we do for this subtracted part, we rewrite it as a sum. So it's I running from 1 to K. Here we have F sub I of B minus F sub I of A. And then here the corresponding, this multiplication here is going to be F sub I acting on A. Now it turns out, I mean, if you were to combine these into one sum, you'd have one sum of this guy minus this guy. But these two, let me get out of the way. This factor here in the combination of the two sums are the same. Okay? And so we can factor that out, and we have F sub I of B minus F sub I of A. And then what we'll be left with for each term is F sub I of B minus F sub I of A. Okay, this multiplication. Well, the same thing times the same thing is nothing more than as I runs from 1 to K. Well, here I'll write down those scores. So it's F sub I of B minus F sub I of A to B squared. And that is the, if we were taking the square root, we have the norm. Of that quantity. So if you will, it is the norm this is equal to, well, if you want, you could say, hey, this is Z acting on anything, now Z bar acting on anything, and that's equal to that's the value of, well, it's in RK, to B squared. So I'm not going to write down RK. It's the norm in RK. Well, I did write it down. That's what we have. Okay, so that was the phi of B minus phi of A. Now, if we apply the absolute value then here's what we get. We get the absolute value of what we have by the mean value theorem. Phi of B minus phi of A has to be equal to the absolute value of B minus A times the absolute value, it was, I think it was Z times F prime, dotted with F prime, acting on some X. Okay. This should be bars, these places. Okay, and I'm talking about taking the absolute value, so this is just in R. Okay, this is just in R, not RK, R. And here, this quantity is absolute value of this, which is nothing more than the norm squared in RK, is going to be equal to the absolute value of B minus A. Well, B is bigger than A, so that's just B minus A. And here we have this absolute value. But I'll expand this with its absolute value, but this dot product is nothing more than the sum as I runs from 1 to k. And again, this is going to be f sub I of B minus f sub I of A. Okay. And then this would be, that's A. And then times, this is f sub I prime acting on X. Okay, now what we're going to do is we're going to use the Schwarz inequality. Oh man, that was in chapter 1. So using the Schwarz inequality, for complex numbers, so what I'm worried about, what I'm working with is here. These are real numbers, but real numbers can be thought of as complex numbers. And so here, let me remind you what the Schwarz inequality is. So it says that the sum as j runs from 1 to k of A sub j, B sub j conjugate, that inside absolute value of being squared is less than or equal to the sum as I runs from 1 to k of the absolute value of A sub j, that's in the complex plane, B squared, times the sum as j runs from 1 to k of the absolute value of B sub j's to B squared. Okay, that's what it says. And so really that says that if I want to get rid of the square here, I take the square root of both parts. And so that part right there is going to be just the norm. So we're going to apply that to that summation here. So this is like the A, and this is like the B. Okay? So we have absolute value of Z, or Z bar, here's what I'm calling it, R K squared is going to be less than or equal to, well, the B minus A holds firm. And here, we have this Z bar times F prime bar acting on X, and both of these are absolute values in RK. That's what we have. Let me stop for a second. Let me go back. I think I was planning on going back. I got a little bit. Here, this is our A. This is our B. So this will be the sum of these guys being squared. Well, that's nothing more than Z bar being squared. We've got to take the square root of it, and so use component. So something like Z bar. That just gives Z bar. That's what that is. This part right here is each component being squared, the square root of that, that's going to be the norm of F bar. So that's exactly what we've written in RK. So that's how we get it. And we have an inequality because we're using the Schwartz inequality. This part got bigger than what it's replacing. Now, if we're dividing everything by the norm of Z bar, then what we get is that norm of Z, RK, what is that? RK should get here, is going to be less than or equal to B minus A times this. Okay? Okay. And this is C bar. This is F bar of B minus F bar of A is less than or equal to B minus A times F prime of X. And that proves the theorem. Ladies and gentlemen, that's all I wanted to do today. Thank you very much for your time and patience.